We know that the net current density due to electrons is equal to drift current density due to electrons plus diffusion current density due to electrons. And we know drift current density is equal to N into Q multiplied by mobility multiplied by electric field, and diffusion current density is equal to diffusion constant of free electrons multiplied by charge multiplied by concentration gradient of free electron. We know that electric field is equal to 0, therefore drift current will be 0. Net current due to free electrons will be equal to diffusion current. Now you have to simply put the values. After calculation, you will find the current density to be equal to minus 1120 ampere per centimeter square. We have ignored holes as it is N-type silicon semiconductor. Therefore, the current will be primarily due to the electrons. For question 2, we have doping concentration 10 raised to the power 14 per centimeter cube, acceptor concentration 5 into 10 raised to the power 13 per centimeter cube, resistivity is provided 60 ohm centimeter, electric field is provided 2 volt per centimeter, and the ratio of mobility of hole to the mobility of free electron is 1 by 2. Intrinsic carrier concentration is also provided, which is equal to 2.4 into 10 raised to the power 13 per centimeter cube, and the concentration of electron is asked. You know that for a compensated semiconductor, the concentration of free electron is provided by the formula Now you simply have to put the values. After calculation, you will find the free electron concentration to be approximately equal to 5.965 into 10 raised to the power 13 per centimeter cube. This question was quite simple, and all this data like the resistivity, electric field, and the ratio was given just to confuse you, as all these values were not required for finding the answer. For question 3, we have acceptor impurity equal to 10 raised to the power 16 per centimeter cube and donor concentration to be equal to 3 into 10 raised to the power 15 per centimeter cube. Intrinsic air concentration is also provided equal to 1.5 into 10 raised to the power 10 per centimeter cube. Doping concentration is significantly greater than intrinsic air concentration. Therefore, the low level injection condition is valid here. So, the whole concentration will be approximately equal to Na minus Nd, which is 7 into 10 raised to the power 15 per centimeter cube. Now, by mass action law, we can find the approximate value of free electron concentration, which will be equal to square of intrinsic carrier concentration divided by whole concentration. And after calculation, you will find the value of free electron concentration to be approximately equal to 3.214 into 10 raised to the power 4 per centimeter cube. For the fourth question, we have to calculate total diffusion current density at x is equal to 0, and we know the diffusion current density due to holes is equal to minus diffusion constant of hole multiplied by charge on a charge carrier multiplied by gradient of hole concentration. Since we are supposed to find the diffusion current density at x is equal to 0, we have to put value of x equal to 0, and also diffusion length of holes is provided 5 into 10 raised to the power minus 4 centimeter. After putting the value of diffusion length in the expression and calculating, we will get the diffusion current density due to holes at s is equal to 0 to be equal to 3.2 ampere per centimeter square. Similarly, diffusion current density due to free electrons is provided by diffusion constant for free electrons multiplied by charge multiplied by concentration gradient of free electron. Here also we will put x equal to 0 and diffusion length of free electrons is provided 10 raised to the power minus 3 centimeter. After putting the values and calculating, we will get the diffusion current density due to electrons at x is equal to 0 to be equal to 20 ampere per centimeter square. So, the total current density at x is equal to 0 will be the sum of diffusion current density due to free electron plus diffusion current density due to holes. Therefore, the total current density will be equal to 23.2 ampere per centimeter square. For the fifth question, we will first find the electric field which is present inside the semiconductor, and we know the electric field is equal to potential drop applied divided by length of the semiconductor. Here, potential applied is 5 volt and the length of the region of the semiconductor is 1 micrometer. Therefore, electric field comes out to be 5 into 10 to the power 4 volt per centimeter. Also, we know that drift velocity is equal to mobility into electric field. Therefore, mobility is actually slope of drift velocity versus electric field curve. And upon considering the linear region, we will find mobility to be equal to 20 centimeter square per volt second. Now we have to find the mobility inside the reference semiconductor, and we know that the drift velocity is equal to mobility into electric field. We just found mobility to be equal to 20 centimeter square per volt second, and electric field we just found to be equal to 5 into 10 raised to the power 4 volt per centimeter. And upon calculating, we will find the drift velocity to be equal to 10 to the power 6 centimeter per second. Now, the resulting current density will be equal to the resulting current density comes out to be equal to 1.6 kiloampere per centimeter square.